Hello everyone, welcome to Math with Allison. Today we're going to be talking about limits and their basic rules. We're not going to quite get into solving them yet, but if you would like to see my previous two videos, I talked about the definition of a limit and I talked about one-sided limits. You can see those are linked right here. So moving into today's topic, like I said, we're going to be talking about basic rules. We're going to get into how we solve those in the future videos, so tune in for more. First of all, we're going to talk about linear functions. So a reminder of a linear function is just a straight line. We have m representing the slope, x is our input, and then b is our y-intercept. When we're working with linear functions, when we take the limit as x approaches some value of a of the linear function f of x, we can also just evaluate it at that value. Because like I said, they're just straight lines. So if we take the limit as it approaches a value, it's always just going to be f of a. That's the case for linear functions. It's not the case for all functions. That's why this is a special case and has its own rule. So I have an example here, f of x equals negative 2x plus 1. We also have the beautiful graph over here for those who like to see visually, including myself. So let's go ahead and evaluate the limit as x approaches negative 1 of f of x. I'm going to write in the limit as x approaches negative 1 of my function, negative 2x plus 1. Notice here that I put parentheses around negative 2x plus 1. That's because we're taking the limit of the entire function. So when it's separated by pluses and minuses, I like to put parentheses to show we're evaluating the entire limit, not just the first part. It's like a whole thing together. So like our rule said, we can just plug in negative 1. Let's go ahead and take f of negative 1. Plug that in, negative 2 times negative 1 plus 1. We get positive 2 plus 1, which is equal to 3. And let's go ahead and check that out with our graph. So my x value is negative 1. I'm going to go to my corresponding y value, which is indeed a positive 3. If I approach it from either side, I'm approaching 3. So this is the case for all linear functions, all straight lines. You can just plug and chug, which is really nice. So now let's go on to our limit laws. So our limit laws, first of all, we have to say they assume that both limits exist. So the limit as x approaches a of f of x and g of x, they both already exist. They're already there. So using this, we can move forward. Let's go ahead and talk about constants, which just mean a number. We have the limit as x approaches a of a value c is just equal to whatever number it is. So whatever c is. We have an example right here. We have f of x is equal to 6, and we're going to take the limit as x approaches 0 of 6. It is indeed equal to just 6. If we think about this on a graph, we have f of x is equal to 6. It's just a straight line. And we chose 0 in this case. X approaches 0. So as we're approaching 0, our function is indeed approaching 6. No matter what x value we choose on the line, we're just going to be approaching that value. So that's really nice. When we just have a number in there, it's just equal to the number. Talking about sum and difference, we have the limit as x approaches a of f of x plus g of x or f of x minus g of x. If we haven't seen this notation before, it just means a plus or a minus. Doesn't matter which one is there, the rule applies to both of them. And that means we can separate it out into two quantities. Instead of having f of x plus g of x on the inside, we can take the limit of each one separately and add or subtract those together. So we have another example here. We have f of x is equal to x, g of x is equal to 1. And here I have f of x plus g of x on the inside. So we could either use our knowledge that, hey, this is a linear function, I could just plug it in, or we can go ahead and apply this rule. I have the limit as x approaches 2 of our first function, which is just x. And now it's kind of like you're distributing the limit if you want to think about it that way. But as x approaches 2 of 1. So now right here, we can use the constant rule that we just learned. We know this is going to be equal to 1. And right here, we can use the linear function that we just talked about as well. This is a linear function, and so this is going to just be evaluated at 2. And so x at 2 is 2. So now I'm going to add those together. I get 2 plus 1 is equal to 3. And so the limit as x approaches 2 of x plus 1 is equal to 3. So now we have another rule, constant multiple rule. So let me scoot this over a little bit. When we have a function and we multiply it by some number c, we can pull that c out. and then we're left with the limit on the other side. So let's see an example of this. We have f of x is equal to negative 3 e to the power of x. So let's go ahead and evaluate this limit as x approaches 0. Using the rule we just learned, I'm going to go ahead and take out that negative 3. I have negative 3 times the limit as x approaches 0 of e to the power of x. And now I can go ahead and evaluate this limit right here. I know e to the x is a continuous function. We have the limit as x approaches 0 of e to the x is just going to be e to the power of 0. I know this because it's a continuous function and I can just plug it in. Anything raised to the power of 0 is a 1. So now using this, I can plug it in. I get negative 3 times 1 is just equal to negative 3. Another rule we have is the product rule. So this is assuming still that the limit of f of x and the limit of g of x already exist. So we have to have that knowledge already. And when we have it being multiplied on the inside, right here, what we can do is we can kind of distribute that limit again. Now we can separate them into two quantities. We have this limit right here of f of x times the limit of g of x. So let's go ahead and see that in action. We have here f of x is equal to 2x, g of x is equal to sine of x. So first I want to make sure both those limits exist before I can use the rule. So we're taking the limit as x approaches 0 of f of x. I'm going to go ahead and plug that in and use the rules that we already know. We have 2x as our limit. Now I'm going to use constant multiple. I can bring this constant of 2 out front, right? So I bring that out, I get 2 limit as x approaches 0 of x. This right here is a linear function, and so when I plug that in, when it's approaching 0, I get 0. So now using these two together, I get 2 times 0 is equal to 0. Now let's go ahead and evaluate g of x. I want to make sure this limit also exists. So I get the limit as x approaches 0 of sine of x. I know sine of x is a continuous function, right? If we were to graph it, it would be like, woo, artiste. And so I'm just going to go ahead and plug in our value. I get sine of 0 is indeed equal to 0. So now I know that both of these limits exist, they both equal 0, and I can use this knowledge. So I'm going to go ahead and separate them out. I get the limit as x approaches 0 of our first function, which is 2x, times the limit as x approaches 0 of sine of x. We already evaluated these limits individually, so I can just plug them in. I get 0 times 0 is equal to 0. So we're happy we got our limit. Quotient rule is pretty similar. Provided the limit of f of x and g of x already exist, we can also separate them out into the numerator and to the denominator. But this one does have an additional rule, which is that provided the denominator does not equal 0. So I'm going to write it up here. Provided the limit as x approaches a of g of x is not equal to 0. So in our previous example, both values equal 0. That would not be the case where we could separate it out like this, because then we would be dividing by 0, and dividing by 0 is illegal. So we have a new function here. F of x is the same function, but now we have e to the power of x, and we change the value that we're approaching. We're approaching 1 now. So I'm going to go ahead and plug it in. Limit as x approaches 1 of 2x. I can bring out that 2 using my constant multiple rule, or if you wanted, you could just use the linear function rule and apply it, whichever works best for you. Both ways are totally correct. We both would still end up with a value of 2. I'm going to do the same thing for g of x. Limit as x approaches 1 of e to the power of x. E to the power of x is a continuous function, so I can just plug in the value. I get e to the power of 1 is just equal to e. So now we know that the denominator, g of x in this case, the limit is not equal to 0. So we can go ahead and apply that rule. Separating this out, I have the limit as x approaches 1 of f of x in the numerator divided by a perfectly straight line. Limit as x approaches 1 of g of x. Let's go ahead and plug in each value. We already did the work. So we have a 2 in the numerator and an e in the denominator, and we're happy. That's all we have to do. Let's go ahead and move on to the power rule. So when our function is raised to some power, then what we can do is we can bring that power to the outside of the entire limit. So we can evaluate just a little part of the function and then raise it to the power. So we'll see this in action. We have f of x equals x cubed. Let's go ahead and take the limit as x approaches 3. So I'm going to plug in my function, x approaches 3 of x cubed, and now I'm going to apply the power rule. I'm going to instead bring that exponent to the outside. So the x stays on the inside, the cubed comes on the outside. Because now right here, I can evaluate this because it's a linear function. I'm going to write that out. It's a linear function. We can use our rule. So I'm just going to plug in 3. X at 3 is 3. So I get 3 cubed, which is indeed equal to 27. So see kind of here how the rules are building off one another. It's kind of nice that way. So we have another rule. This is the last one for us. It's fractional power. This one's a little different. It's similar to the power rule where if our function is raised to a fractional power, we can bring that fractional power to the outside and evaluate the inside, kind of like how we do a linear function. But this one has some more requirements for it. So let's go ahead and talk about them. First, we have that f of x has to be greater than or equal to 0. When we start working with negative numbers and we raise them to different powers, they can alternate between positive and negative. So take negative 1, for example. If you square it, you get positive 1. If you cube it, you get negative 1. So we don't want to be oscillating. For that kind of similar reason, the m in the denominator right over here, this m, it has to be even. The last thing is that n over m has to be fully reduced. So we're going to work that out in this example over here. We have f of x is equal to 8 over 12. So I want to make sure I hit all of these requirements. So let's go ahead and first reduce 8 over 12. So I'm going to write this out. I get x, and then I'm going to take a 2 out of both of them. I get 4 over 6. I'm going to take another 2 out of both of them because that's not fully reduced. I get 2/3. So am I able to use this? No, I'm not. So that means I cannot apply this rule. I'm going to write out that big no. Let's go ahead and take another example where we can. I'll just write it out, x to the 1/2. We have that it's fully reduced, we have that the denominator is even, and our function is greater than or equal to 0. So we'll write that out. X is greater than or equal to 0. So let's go ahead and apply our limit. Let's take the limit as x approaches 1 of f of x. We're going to plug in our f of x. We get x to the 1/2. And now I'm going to apply that rule, which is very much similar to the power rule. I can take out that exponent from the x to the whole limit. And so now I'm going to go ahead and evaluate this like I do a linear function. I get 1 to the power of 1/2, which is indeed 1. Thanks for watching. If you all enjoyed the video, please leave a like. Please also leave in the comments other types of videos you'd like to see, other types of problems you'd like to see worked out and evaluated. And yeah, that's all I have for you all today.